Hello learners. So today I'll be sharing my concepts related to stability analysis of the control system. So how do we define the stability? A linear time invariant system is said to be stable if the output eventually comes back to its equilibrium position after disturbances. And it is said to be unstable if the system output continues to oscillate or increase unboundedly from equilibrium state under the influence of disturbances. So it means in case the system comes back to its equilibrium position after disturbances, it is stable, otherwise it is unstable. The stability for the linear time invariant is judged with the help of the two criteria. First is the Bibo criteria, that is termed as bounded input, bounded output. If bounded input is resulting into the bounded output for a control system, then it is said to be Bibo stable. And in case, in the absence of the input, the output has a tendency to go to zero value, irrespective of initial condition, then the system is said to be asymptotically stable. So these are two main criteria for the ascertaining the stability of a control system. This can also be expressed in terms of impulse response of a system. The output is said to be bounded if the impulse response of a system is absolutely integrable. That is, ht dt is, in case we take up its integral, it comes out to be less than infinity. Then the nature of ht is the transfer function. It depends on the poles of the transfer function hs, which are the roots of the characteristic equation. It means that stability of a linear time invariant system is affected by the position of the roots of the characteristic equation. So just look at the impulse response corresponding to the location of the roots of the characteristic equation in the S-plane. This is one root, that is, this is the S-plane. Sigma is the real axis, j omega is the imaginary axis. Here we are having a pole that is lying in the left half of the S-plane, and there is another pole that is lying in the right half of the S-plane. In the case of the this position of the poles, for this pole, the output has a tendency to come to zero value corresponding to the impulse input. And corresponding to this location, the output has a tendency to rise. It means that this position of the root of the characteristic equation is making the system unstable, although this position is making it stable. Then let us consider. So this is a root lying in the left half of the S-plane. It is making the system output to decay to zero value in the absence of the input. And this position of the root is making the system output to increase even in the absence of the input. Then this is another location of the roots of the characteristic equation. These are the complex conjugate root lying in the left half of the S-plane. Corresponding to this, we get a oscillatory response that is exponentially decaying. So ultimately, it is dying towards the zero amplitude. But in case the same conjugate pair of root lie in the right half of the S-plane, there the envelope of this oscillation, it keeps on increasing. Ultimately, the system output is going out of bound. Then in case, the third case is that we are having single pair of roots on the j omega axis. So corresponding to this, the system is having oscillatory response. This is the amplitude of the response will decide whether the system is stable or not. In case the amplitude is coming out within the stability bound, then the system is stable. Otherwise, the system is unstable. So in such a cases, the system is said to be marginally stable. If this amplitude is within the amplitude of this oscillation is within the margin of our stability, then the system is stable. Otherwise, it is not. If we are having double pair of roots on the j omega axis, means repeated roots on the j omega axis, then we can see that response is oscillatory and the amplitude of the oscillation is increasing with time, that means the system is becoming unstable. Then we are having single root on the j omega axis. It corresponds to a fixed response. So system is said to be marginally stable if this much amount of the output corresponds to the margin of stability that is defined by us. But if we are having repeated root on the origin, then that result into an output that keeps on increasing. So it means that system is having a tendency to become unstable. So from this diagram, it is clearly visible that if the roots are lying in the left, roots of the characteristic equation are lying in the left half of the S-plane, then the system is stable. If any one root of the characteristic equation is lying in the right half of the S-plane, the system output is going out of bound. So the system is becoming unstable. If we are having non-repeated roots on the j omega axis or on the origin, then the system is marginally stable. That is being shown by this response as well as that fixed amplitude response. And in case we are having repeated roots on the j omega axis or on the origin, then the system response increases and it becomes out of bound and the system is unstable. So this is the from this response, these responses we can very well judge that the roots of the characteristic equation completely describe the behavior of the system. So the necessary condition for stability becomes this, since when we are saying that all roots of the characteristic equation should lie in the left half of the S-plane. So that condition is satisfied in case all the coefficients of the characteristic equation of the linear time invariant system, they are non-zero and they are positive. And none of the coefficients should be zero. Means all of them should, all coefficients of the characteristic equation should have the same sign. Only then that condition that the root lying in the left half of the S-plane, all roots are lying in the left half of the S-plane. If there are sign changes in the coefficients of the characteristic equation, it means that some root are lying in the right half of the S-plane also. That we can see here also. In case the root is here, then the response is simply having a tendency to become zero in the absence of the input. When we are having this complex conjugate pair of roots, again the system response has a tendency to become zero ultimately. And again, if we are having a root over here, again it's decaying with respect to the time. So in case we are having all roots of the characteristic equation lying in the left half of the S-plane, then the system is stable. And for that, it is essential that all the coefficients of the characteristic equation have the same sign, either positive or negative. So one way, this is not the this is the necessary criteria, but this is not the sufficient criteria. In order to check up the this one, the stability of the system, we use, in order to check the sufficient criteria, we go for the two tests. First is the Hurwitz stability criteria and second is the Routh stability criteria. So in case the system characteristic equation is given as A naught s to the power n plus A1 s to the power n minus 1 and so on, then we just define a Hurwitz determinant like this. First of all, it is written A1 A naught, then A3 A2 A1 A naught, then up to A2n minus 1, A2n minus 2 up to An. First of all, we'll form the Hurwitz determinant in this manner. Then the necessary and sufficient condition for stability is, because we want to establish the sufficient condition for stability. That criteria is not sufficient, like that we have stated in the previous slide, that all the coefficients are non-zero. So in order to establish the necessary as well as sufficient condition for stability, what is required? That all the principal minor of this Hurwitz polynomial, they are greater than 0. So principal minor will be formed by A1, then it will be A1, A2, A0, A3. This one. So it will be formed by This is another principal minor, then next principal minor, then next principal minor, and so on. If all the principal minor of the Hurwitz determinant they are positive or they are greater than 0, then we'll say that the system is stable according to the Hurwitz stability criteria. Then another criteria for ascertaining the stability of the linear time invariant system is the Routh stability criteria. For that, let us consider a system whose characteristic equation is given by Fs is equal to a naught s to the power n plus a1 s to the power n minus 1, and so on up to an equal to 0. So first of all, we'll make up the Routh array. Within this a naught, then we leave one coefficient a2, means we'll just put up these coefficients. These are the even coefficients, and in the second line we'll write down the leftover coefficients. Then after that, in the second line, in the third line we'll write down b1, b2, b3. And how do we write down the b1, b2, b3? It will be written as b1 will be equal to a1, a2 minus a naught, a3 divided by a1. So this b1 will be equal to a1 a2 a1 a2 minus a naught a3 divided by a1. Then b1 will be equal to a1 a4 minus a naught a5 divided by a1. Then b3 will be equal to a1 a6 minus a naught a7 divided by a1. Then similarly, we'll get the values of c1, c2, then and so on till we reach to the, because first of all we have to write down all the entries starting from s to the power n, then we'll keep on increasing up to s to the power 0. We'll complete this Routh array, and once the Routh array is established, then total number of sign changes in the first column of Routh array, it gives the total roots of the characteristic equation lying in the right half of the S-plane. In case there are no sign changes after making this Routh array, there is no sign changes in the value of these coefficients within the first column, then the system is stable because no root will be lying in the right half of the S-plane. But in case there are sign changes, then total number of sign changes indicate the presence of the roots in the right half of the S-plane. So the advantages of the Routh criteria is that obviously in case there is not a Routh criteria, how will we ascertain that the system is stable? We'll calculate the roots of the characteristic equation, but in case that is only possible in case up to the equation is of the order of order 3 or 2. Otherwise, as the order of the equation increases, it will become very difficult for us to solve it to get the value of the uh, uh, roots of the characteristic equation. So when we are using the Routh criteria, we need not solve characteristic equation to get its roots. And in case we are using the Hurwitz criteria, then we have to evaluate a number of determinants that is not required in the case of the Routh criteria. And with the help of the Routh criteria, we can easily judge the relative stability, and we can easily calculate the critical gain and the frequency of the sustained oscillation. And we can easily get the range of the gain for the stable operation of the system. And Routh criteria is also used to get intersection point of the root locus with the imaginary axis. For example, it is one of the example is taken over here. This is the characteristic equation. So we have just formed up the Routh array starting from S5 to S0. So we have just started up 1, then we are having 3, then we are having 1, then S to the power 4 is 6, then 2, here also 1, and here we are having 2, then S3, this is 6 into 3 minus 2 into 1 divided by 6, so it will be 2.67. Similarly, we'll complete this Routh array. Within this Routh array, total number of sign changes is equal to 1, because positive, 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 then positive to negative 1 change, then negative to positive another change. So it means there are two roots of the characteristic equation which are lying in the right half of the S-plane. So the system is unstable. So this is one of the example of the Routh array. Then let us take up the certain cases of the Routh array, because when we are making the Routh array, then certain difficulties arise. Like, let us consider that characteristic equation is given by SQ plus S plus 2 equal to 0. Then the Routh array will be written as 1. Then it will be equal to the coefficient of S cube. This is 1 and this is 1 here. Then this is S square will be getting 0 and 2. Then just look at this. This is 1 and this is 1. Then S2 coefficient will be, because S to the power 3 plus 0, just look at this, why this 0 is present over here. This is S to the power 3 plus 0 into S square plus 1 into S plus 2. So 1 and 1. These are present over here. And in the second row, we are getting 0 and 2. Because the coefficient of S square is 0 and coefficient of S to the power 0 is 2. Then when we want to get a coefficient here, it will be 0 into 1 minus 1 into 2 divided by 0. So that will result into the infinity. So what we'll do, when first element of the Routh array becomes 0, then it becomes difficult for us to get the next elements. In such cases, we replace 0 by epsilon. That is a very small number that is approaching 0. So S to the power 3 is equal to, so we'll just rewrite it, replacing 0 with epsilon. So we have replaced 0 with epsilon. Then we'll complete the Routh array. Then we'll get the value of these quantity as epsilon is tending to 0. So when epsilon is tending to 0, it will be positive. And when epsilon is tending to 0, this is negative. So total number of sign changes will be positive, positive, negative, then positive. So it means total number of sign changes is equal to 2. So number of the roots of the characteristic equation lying in the right half of the S-plane are also 2. So the system is unstable. So whenever the first element of the Routh array becomes 0, then we'll just replace it by a small number epsilon. Then we'll complete the Routh array. Then we'll get the values of all the entries on the first column of the Routh array by substituting limit of epsilon as tending to 0. Then we'll check the total number of sign changes, which will tell us about the total number of the roots of the characteristic equation lying in the right half of the S-plane. Then second case, when any one row of the Routh array becomes 0. Here you can very well see this is the characteristic equation of the system. Within this is 1, 24, then minus 25 we have written, then 2, then 48, then minus 50 we have written. When we calculate the next entries, it will be 2 into 24 minus 48 into 1 divided by 2. It will be 0. Similarly, this when we calculate, the next entry will also come out to be 0. When all the entries of a row in a Routh array become equal to 0, then what we'll do, we'll write down the auxiliary polynomial by looking at these entries within the Routh tabulation, which are not 0. We can write down the auxiliary equation. So this is 2s4 plus 48s square minus 50. So this is the auxiliary equation that we have written. Then we'll take up the derivative of the auxiliary equation. So it will be 8 into 8s cube plus 96s. It will be the derivative of the auxiliary equation. So this derivative will be replaced over here. So s to the power 3, earlier we had 0 and 0. We have written the auxiliary equation corresponding to this row. Then we have taken its derivative. Then what entries we are getting in the derivative, that are being written over here, 8 and 96. Then we'll just complete the Routh array and we look at the sign changes. Total number of sign changes in the first column of the Routh array is equal to 1. So it means that one root of the characteristic equation is lying in the right half of the S-plane and the system is unstable. In case these sign changes, there is no sign change in the first column of the Routh array, even then we will have to check the roots of the auxiliary equation so as to ascertain the stability of the system. So auxiliary equation is 2s4 plus 48s square minus 50. So if we get its root, we'll get its root at s equal to -1, s equal to +1, s is equal to minus j root of 5, and s equal to plus j root of 5. It means that the system is, the roots of the characteristic equation are also telling that the system is unstable, because at s equal to +1, we are having a root. And in case any one of the root is lying in the right half of the s plane, the system is unstable. So we can first of all judge the system behavior from the first column of the Routh theory. Even with in such case, we have to judge the behavior of the system by looking at the auxiliary equation also. We have to calculate the root of the auxiliary equation, because the roots of the auxiliary equation are the roots of the characteristic equation also. And in case some of this root of the auxiliary equation is lying in the right half of the S plane, the system is stable. The system is unstable. Then this Routh array can also be find the range of value of gain for which the system is unstable. System is stable. So this is the open loop transfer function. In case we are having a closed loop type of the system, for that we are having two type of the transfer function: open loop transfer function and closed loop transfer function. Open loop transfer function is given by GSHS, and closed loop transfer function is given by GS divided by 1 plus GSHS. So this is the open loop transfer function, and the characteristic equation is given by this. So characteristic equation is written here, and then Routh array is formed in the way that we have discussed. Wherever we are having k, we'll just write it as equal to k. For the system to be stable, all the entries on the first column of the Routh array should have the same sign. So 1 is positive, 6.5 is positive. So for the system to be stable, this entry should also be positive, and this should also be positive. That is greater than 0. So we get two things over from here, that k should be greater than 0, and the range of the value of k should lie between 6.0 to 6.5. So likewise, the Routh array can also be determined the range of the value of the gain for which the system is stable. So it's very helpful to us. It directly gives us the view about the stability of the system, and the total number of calculation involved, they are very much reduced. And also we have discussed a number of advantages of the Routh stability criteria. So it's very helpful to us in that way. So thank you very much for your patience learning.